All right. Hey guys, welcome to Module 5 of Intro to Neurotechnology. This is a module on artifact correction and rejection. So going off of Module 4, which was on filtering and Fourier analysis, artifact correction and rejection is also another important step in signal preprocessing and in general just processing the data, processing the raw data before you can actually use it in some sort of algorithm, product, or application. So first off, what is an artifact? So an artifact is basically any signal that is recorded by the EEG, but that is not generated by the brain. So for example, in this diagram below, you can see that you have the observed EEG signal over here. And the things that are contributing to that are, of course, the brain signal that we get. But we also have other things like eye movements, eye blinks, muscle movements from our neck and our jaw, or cardiac, so our heartbeat, can interfere with all of these signals. In addition to that, we also have signals from external devices. So the computers that we're using, our phone in the room, the lights that we're using, anything that has a circuit basically, or any sort of electrical activity that is big enough to be picked up by the EEG, but that is not generated by the brain specifically, is considered an artifact. And so there are three main problems with artifacts. The first is that it decreases the signal to noise ratio. So if you remember from module 3, when I first talked about signal to noise ratio, the EEG system is a system of relativity. And that might not be the best way to describe it, but the way I think about it is everything is relative to other things. It's not absolute. So the signal is relative to how much noise there is. The signal is only as good or can tell you as much information depending on how much noise is polluting it. So you want to maximize that ratio. And the more noise you have, the more artifacts you have is obviously going to decrease that ratio. Another thing that is problematic with artifacts is that they may be systematic. And so averaging will not do anything. Again, if you remember from module 3, I talked about averaging, where we use averaging as a technique to eliminate all the minuscule blips that occur in an EEG waveform. So if you remember, I said that you're often trying to find a pattern, or like the ERP component or waveform. And those are like overarching patterns that are easily visible. And those little blips that occur along are like voltage spikes and voltage deflections. And when you average the positives and the negatives, what remains is a systematic pattern. Well, if the artifacts themselves are systematic and they're occurring because of certain reasons or because of certain constant factors like blinking or your phone is in the room or something like that, those are systematic factors that aren't going to be removed from the averaging process. Instead, they'll probably be magnified because they're systematic in the first place. Um, Another problem is that they can cause a potential change of sensory input across the experimental conditions. So if you blink, for example, or if your eyes aren't focused on the right part of the stimulus when you're looking at it, or if they move during an experimental condition, these are all things that'll affect the experiment as a whole. And these are all artifacts that are not exactly measuring what we want it to and are interfering with the actual noise. So now that you know the three main problems, there are two main ways to go about this. One way is to just straight up remove the artifacts, which is called artifact rejection. And the other way is called artifact correction. And we'll go over the different techniques and the pros and cons of each one. So some basic characteristics of an artifact. First off, the most common kind of artifact is an eye blink, right? And why do eye blinks happen, or like what is happening when you blink your eyes? So the movement of your eyelid closing momentarily creates a voltage deflection, and a large electrical potential is created between the cornea at the front of your eye and the retina at the back of your eye, and this deflection creates a dipole. So the eye blinks, or like when you blink your eye, it differs in polarity between the top part of your eye and the bottom part. So if you remember, I said when we looked at EEG systems that we have electrodes that are obviously on your scalp and on your head, but we also have reference electrodes, usually two behind the ear, two on the temporal regions, and a couple on the forehead. So, and one right below your eye. So if you look at those electrodes, you'll see that the ones on your forehead are differing and are polarly opposite to the ones that are below your eye. And that's because the blinks, or like specifically when you blink, and that's because the blinking creates a difference in polarity. And we use this to our advantage to help us identify eye blink artifacts from any other sort of artifacts, because most other artifacts tend to maintain the same kind of polarity throughout the scalp distribution, whereas eye blinks switch polarities. And so that is basically what happens when you blink your eye. You create a voltage deflection. You create a difference in polarity between the electrodes above your eye and the electrodes below your eyes. And we use those characteristics to be able to isolate eye blinks from any other sort of components. And the reason this is important is because you don't want to remove all artifacts. You only want to remove the ones that reduce your statistical power or create confounds. If you were to remove every single artifact that you encountered, whether it be through external devices like machines or any circuitry, or like any sort of muscle movements or cardiac movements, you would basically be left with very little clean parts of your data set. And that would drastically reduce the validity of your results. So you want to strike a balance between like how much you're cleaning and how much you're taking out and processing your data set, and how much of the actual raw elements you're leaving in it. Because the more you tinker around with it, the lower your validity gets. Um, you also want to discard all channels for that given time period during which an artifact is present. So usually what happens is you take a raw EEG, right? Just a pure stream of continuous data. And you, as the experimenter, know when the stimulus was given and what experimental trial was what. So you divide that data into segments, and we call those segments epochs. And so you have like each trial representing a certain epoch. And let's say on trial 2, we detected an eye blink. So because of the superposition problem, if you remember from earlier, where every single where every activity in the brain, or every signal or generation site, is picked up by electrodes around the scalp at different intensities. So using that property, that means every single eye blink that you do will affect every channel to some varying degrees of intensity. And so that's why we remove all channels within that given time period. So we would just eliminate trial 2 if we were doing artifact rejection and we detected the artifact, because the artifact will be present to a certain extent in all channels, and that would affect the results. Also, it doesn't make sense to remove one out of the 64 channels of just one trial and continue doing your process, because you want to have the same amount of channels for every single trial. Otherwise, that's just kind of like a bad design for data analysis. So one important thing that you need to know before we go on to artifact rejection is baseline correction. And as the name suggests, baseline correction is important because it creates a baseline for the whole wave form. So what this means is the EEG data is a continuous stream of data, right? So if you look at this picture here, you can imagine it continuing on the right and being continuous on the left. And EEG data is not constant, and we have constant voltage differences. So the idea of using a baseline correction is to subtract all the pre-stimulus voltage from the beginning of every single trial, average all those pre-stimulus voltages, and then subtract that from the baseline. And this is important because if you remember, the whole point of event-related potentials, or ERPs, is to compare the electrical potential at a stimulus to its pre-stimulus activity. It's all relative. We want to know the difference in activity between when the brain is doing nothing versus when we give the brain a specific task or a specific stimuli to look at. So if we want to compare the differences between a baseline activity and a stimulus activity, we want to make sure we have a solid baseline to even compare it to in the first place. And the best way to do that is to take the pre-stimulus activity for before any given trial, average all of them, and then subtract that from the overall waveform. And if you do that, you'll see the difference that you see over here. In fact, when you subtract it, when you subtract the baseline activity and do baseline correction, you kind of reset the wave to 0, so that when you're starting your analysis, everything is relative to that baseline period. And that's very important in actually being able to interpret the results in the first place. Because this waveform is meaningless without knowing like what the baseline activity was in the first place. So now that we have that, there are 3 main methods for artifact rejection. And it's the absolute threshold method, the moving window peak-to-peak amplitude, and the step function. So the first one is the absolute threshold method. And this is the most primitive of the methods. It's a very crude way of detecting and processing the data. So how it works is you basically set a threshold value of a voltage. So over here, for example purposes, I drew a line right here, and this is your threshold, right? It's just a flat line that you set as your number. And the crossing of that value during any trial means that there's an artifact, that an artifact has been detected. And if we're using artifact rejection, that means we're rejecting all the channels, all the electrodes within that given trial for that time period. And of course, when you look at it, baseline correction is necessary for this method to make sense in the first place. And here's why. So if you never baseline corrected in the first place, you might have that threshold is meaningless because it's all relative to like what the baseline was. The threshold is like obviously a relative to the baseline where it started at, and if you never corrected for it in the first place, you would have a lot of false positives and even misses in your data set. And what I mean by that is, like, if you look at this example, if I did not correct for baseline and I had this waveform up here, the one that's the one that's at the top, it seems to be crossing the threshold, and I would label it as an artifact. But baseline correcting it now sets it down to 0, or gives me, or it's referencing it to its baseline. And now if you look closely, it's actually right under the threshold value. So I would not label it as an artifact. So if you're going to use the absolute threshold method, you want to make sure you do baseline correction before it. Otherwise, you'll be making wrong judgments on what is or what is not an artifact. But the reason this method is so crude and so primitive is because it's very absolute. And so I'll keep reiterating this again, but the whole premise behind ERPs and EEGs is that it's all relative. So having an absolute number where you just set an arbitrary constant and you're like, if it crosses this value, then it's an artifact, is the wrong way of looking about it, because it doesn't contextualize immediately what is happening immediately before and immediately after. And that's very important because voltages continue to change throughout time, and you want to look at, like, what's happening right before or right after, instead of setting a random high number that's your threshold value. So the second method of doing it is called a moving window peak to peak amplitude. And it's kind of a long name, but it's not terribly hard to understand. So the idea behind it is that you choose a window of constant length or constant time interval. So let's say 200 milliseconds. And you take this continuous waveform that you're seeing here, and you divide it into chunks of 200 milliseconds each. And so that's your window. And what you want to do is overlap windows with one another with just a certain constant time factor. So let's say our first window was from 0 to 200 milliseconds. Then our next window could be from 100 to 300 milliseconds. So I'm overlapping the first and second window with 100 milliseconds of time interval. And the idea behind this is that if you increment each window across the whole time wave, across the whole waveform, and you overlap it, the chances of you detecting an artifact are pretty much guaranteed, because you are overlapping each window and the window is not too big in the first place. So it will probably span the whole length of the artifact. For example, eye blinks are usually last about 200 milliseconds. So if your whole window width is 200 milliseconds in the first place, you would be able to detect that whole, deflection jump within that given time interval. So what you want to do after you have all those windows is you look at all the peaks in the window and you find the biggest difference in amplitude. And if the difference in amplitude is greater than a certain threshold, a difference between consecutive amplitudes is greater than a given threshold, you label it as an artifact. And so this method is way better than the absolute threshold method because it's taking into consideration what happens immediately before and immediately after a given amplitude. And so it's kind of contextualizing the waveform, which is really important because everything is relative. So by doing that, you are able to detect the large deflections in blinks because they happen between consecutive amplitudes. And instead of setting an arbitrary threshold that they're crossing, you're able to compare like before what the peak was before it actually jumped or before it dropped to a certain level. Another way of analyzing eye blinks or artifacts is called a step function. So if you remember from earlier, the eye blinks are voltage deflections that change polarity, right? The electrode on your forehead is going to be positive versus the electrode below your eye is going to turn out negative, or vice versa. So the step function takes advantage of this polarity difference above and below the eyes. And what it does is it finds the largest difference in mean voltage between consecutive 100 millisecond intervals. And what that does is subtracting the difference creates a much larger value, and it looks something like a step function. So if you're looking at EEG data, you'll see like these continuous waveforms, and then suddenly just spike or suddenly drop and continue at that same level. And same thing with any sort, even if you don't use this method, that's typically what you do see when you look at EEG data and eye blinks. You'll see like just large blips randomly. So I did some basic math here just to illustrate the principle so it's more clear. So imagine X is the electrode that is above your eye and it's positive, and Y is the electrode that is below your eye, so like right on your cheek right here, and that's negative. So subtracting them, you actually end up with the sum, and that's a far greater value than either of these individual ones combined. And if you flip that around and you say the top one is negative and the bottom one is positive, while you subtract them, you end up with the number that is far more negative than either of these numbers combined individually. And so that's why you get the step function that helps you analyze and cleanly pinpoint like where the artifact is and be able to extract that feature out of that. So to summarize, we went over the three methods of artifact rejection: absolute threshold method, the moving window peak to peak amplitude, and the step function. And these are all, the absolute method is, very crude. I wouldn't recommend doing it, but the other two are fairly good and they're fairly reliable. And basically what they do is just identify where the blinks happen, and you can basically cut that whole chunk out of your data set when you're processing it. And there are scripts to do all of that. But there are also three methods for artifact correction. So if you remember from earlier, there are two things you can do when you have an artifact. You can either throw it out or you can correct it. And there are three ways to do that. The problem with artifact correction in general is that there's no margin of error that we can use to kind of say how off we are. So all of these methods of correction are done with statistical modeling and basically trying to estimate to what extent is the artifact influencing the data set, and then subtracting that from the original waveform. So we're basically trying to subtract out all the artifact values from the original wave. And this is all done with modeling, and there's no like margin of error. There's no way for me to say like, oh, by doing this, I'm compromising my accuracy by maybe like 10% or 15%. There's no way to quantify that, and so it's very iffy to know how far off we are, or like to what extent this influences the actual data. So that's pretty much the only drawback, but it's actually a pretty significant one. So the first way of doing it is a regression-based procedure. So this is where the artifact generated in the eyes are propagated to the scalp site in a very predictable manner. So the artifact-related voltage, like basically the EEG coupled with all the artifacts that you are seeing, is basically the size of the artifact recorded times a weight factor, as you're familiar with that concept already. So the basic premise of this regression-based procedure is basically to subtract a factor of the EOG activity from the ERP waveform at each scalp site. And EOGs are basically the electrodes at or around the eyes, or that pick up ocular activity. So what you want to do is subtract that ocular activity, subtract the factor of that ocular activity from the actual waveform. But the problem with this, like I've said before, is that electrodes on the brain don't correspond one-to-one with other components. So the EOG, that is, even though it's on your eye, it's like in your temporal lobes or right under your eye, is capturing your eye activity the most, the blinks at the most intense level, but it's also capturing brain activity. And so when you subtract EOG activity from the original ERP waveform at any of these scalp sites, you are also subtracting part of the brain's response, and you are changing the actual data that you have. And so that's one of the biggest drawbacks that affects the validity of your results as well. So as you can see, everything is very intertwined with each other, and it's very hard to isolate what exactly you're looking at, which is one of the biggest drawbacks or one of the biggest complications of EEG research. Um, Another way you can do it is actually I want to go back to this slide 1 second. The second method of doing it is dipole localization. However, dipole localization is a very intense process. It requires around like they recommend having like 7 electrodes around your eyes, and it's pretty complicated. So I'm not going to go into that for the sake of time. And it's honestly not feasible for what we're going to be doing because we don't have the kind of devices or hardware to have 7 electrodes around the eyes. But if you want, you can look more into that. What I am going to do is move on to the third one, which is statistical component isolation procedures. So specifically, there's something called independent component analysis, which we refer to as ICA. And the basic idea of this is the idea that artifacts have a fixed scalp distribution. So whether your brain is focusing on something like paying attention, or it's looking at something like a visual stimulus, or it's doing some sort of task, you are going to blink or you are going to have artifacts. And those artifacts have independent characteristics that are independent of the ERP waveform. So regardless of what your brain is doing, you'll always be blinking, and those blinks have characteristic scalp distributions that are unique to that and independent of what the task is being done. So what you want to do is use statistical analysis to isolate those components, those independent characteristics. And then to remove the artifact, you simply reconstruct the data by adding together all the non-artifact related components and leaving out the ones that you identify. And so it sounds pretty simple with statistical modeling. But like I said, one of the big drawbacks is not having a margin of error sort of way to gauge how accurate you are. So how ICA works, basically, if you remember the superposition problem, you already know that waveforms are a combination of ERP components and their weights. So if you have S number of sources or generation sites, and you have E number of electrodes, so 32, 64, or 128, the weights form a matrix if you line them up. And what we call this is the mixing matrix. The goal of independent component analysis is to find an unmixing matrix that gives you the source components as a function of time. So if you want, it's better understood if you look at this diagram. So if you've seen this before, right, you have these waveforms, you have these source components, you have these weights, and you have these waveforms that are observed. This is what we call the mixing matrix. So if you have the number of electrodes and all the components, and the values of the matrix are the weights linking each electrode to each component. And so the goal is you want to find an unmixing matrix that can simply give you these components as a function of time. You start off with this, and you already know this, and you want to find an unmixing matrix that you can use to come to this idea. And what this lets you do is now you've isolated all the components, one of them being the artifacts, or if you have eye blinks, one of them being the eye blink component. And then you can reconstruct the data by leaving that one out. So how do you actually go about finding the unmixing matrix? So the independent ICA figures out the unmixing matrix by looking at statistical relationships between all the EEG channels. And it's important to know that it doesn't actually know anything. It has no knowledge of where the electrodes are placed or the time sequence. It's kind of blind to all those things. We're just feeding it data, and that's all it knows. And so it uses a neural network to kind of learn an unmixing matrix from the statistical properties. There's a lot of math that goes into it, and it's a fairly complicated model, but for all intents and purposes, that's basically how it works. And what you want to do is make sure that the components are maximally independent. And so, there's a typo. Anyway, you want to make sure that the components are maximally independent. So what you want to do is ensure that each component does not provide any info about the value of another component at another time. So if you were to plot this on a scatter plot, basically you should see no correlation, positive or negative. And that's important because these components, if you know, are independent of each other. Like they're being generated in the brain at different locations, and they represent different things. So you want to make sure that the statistical model you're using isn't correlating things that are not correlated in the first place. And so if you look at this flow chart, this kind of helps you solidify and visualize what exactly is happening. So this is what we start with, right? We have time in milliseconds, and we have channels. You see how we can have 32 of them, 64 of them, 128 of them, it doesn't matter. But this is what we start with. And what you want to do is find an unmixing matrix that takes the channels and the components and identifies the relationship between them. And if you multiply these two together, you can decompose it into components as a function of time. If you remember from a couple of slides ago, that's exactly what I said the goal of statistical procedures were. We want to generate the ERP components as a function of time. And the cool little thing is that you can also know this mixing matrix, right, from earlier. That's the one that you start off with. And that is the inverse of this unmixing matrix. So this whole thing is kind of like a big feedback loop, and they're very connected. But the basic idea is that you start with this, you use ICA to generate this, and multiplying these two together will give you the components as a function of time. And then what you can do is isolate the eye blinks and then recompose the data by excluding all the artifacts. So we've covered a lot of different orders of processing, right? If you combine this module and the previous module, and to an extent module 3, we've covered so many different concepts. We've covered averaging, we've covered filtering and Fourier analysis. Now we've covered artifact correction and rejection. So I want to go over like what is the order in which you approach all of this, and what is the recommended way. Well, first of all, when you start off with an EEG wave, you usually want to do a high pass filter to get rid of drifts. So if you record for a long period of time, the voltage kind of, if you look at from beginning to the end of recording, you'll find that the voltage kind of tends to drift either slowly upwards or downwards. And that's because of constant changes, constant slow changes between, mainly by skin potential. So, us sweating or just our skin electric conductivity changing causes these slow drifts. So you want to do a high pass filter. If you remember from module 4, the last one, a high pass filter basically stands for allowing allowing high frequencies to pass and stopping the low ones. So maybe like a frequency of high pass filter of 0.1 hertz to stop all the low frequencies and pass all the ones higher than that. Then what you want to do is you can do averaging, baseline correction, and low pass filtering in any order. Those are linear processes. At least averaging and baseline correction are linear processes. And what I mean by that is just like in math, how you have the hierarchy of things you can do, like addition and subtraction are linear, but multiplication and division are at a different level. Same thing applies here. So you want to do low pass filtering to continuous waveforms, and averaging and baseline correction is also done to continuous waveforms. After you've done that, you want to epic the data into trials. So you already, as the experimenter, you already know like when the stimulus is shown, when what trial represents what condition and stuff like that. So then you want to chunk up the data into relevant parts so you can compare and contrast the control group from the experimental group. Or depending on any sort of product or application you're doing, you might want to separate the data so you can train them separately or put different algorithms on them. So you want to epic the data after you've done all those things, because averaging, baseline correction, and low pass filtering are done on continuous segments of data. And then after you've epicked it, then you want to go into artifact correction and detection. So you can either remove the eye blinks, you can use ICA to statistically model it and fix it, but just beware of all those procedures. But that's basically the general idea of it. A couple things that could change is filtering and artifact rejection. So in some cases, applying filters helps detect artifacts, and in some cases, applying filters makes it harder to detect artifacts, depending on what exactly you're trying to detect in the first place. So that changes depending on your data set and what you're looking for, but those two things could be switched around, and judgment is basically the best way to go about that. So as an overview for this module, we first started off with covering artifacts, like what they were, how that influences data, and the most common artifact, which is eye blinks, and like the scientific reason behind, or like what they actually do to the data, which is the voltage deflection and the dipole that's generated between the cornea and the retina. And then we went over artifact rejection, right? There are three methods of doing it. The first one is the most primitive. It's a crude way, not recommended. The second two, the last two are good, and either one works, depending on your preference. Then we went over artifact rejection, or artifact correction, sorry, with regression-based procedures and statistical component isolation. The dipole localization one, as I said, I wouldn't go over, but you're more than welcome to look into that. And then we went over orders of operations to see like which processing steps should be applied in which order. So yeah, this is all we have for Module 5. Please be sure to fill out the self-evaluation form and look out for the next module next week.